later on. But for the moment being, let's keep it and keep the results intuitive. Okay, so first thing is we need, it's something I've already mentioned kind of last week, and it's we need a criterion for sustainability. So what is sustainability, okay? And then the second issue is related with the production possibility set, okay? So what is sustainability? What is sustainable development? Okay, here I'm going to use the kind of old-fashioned definition of sustainability. So the only thing that we are interested here in is non-declining per capita consumption or non-declining per capita capital level. Okay, so this is what we mean here with sustainability. So here the issue will only be on intergenerational justice. Okay, so we are concerned about future generations' well-being, and that's why we take this into account when solving the intertemporal trade-offs. Okay, so remember something I've already discussed last week. So the more you consume today, the less is get invested, the lower the amount of capital that's built up, so the fewer consumption possibilities that you have. And also the same for the non-renewable resource. So the more of the non-renewable resource that you consume today, the less is available tomorrow, and therefore the lower the production possibilities tomorrow. But these are the intertemporal trade-offs we're going to solve later on formally, and clearly they impact on this definition of sustainability. Okay, because remember, here we are concerned about future well-being and therefore how much can be consumed and produced tomorrow. Okay, that's what we are concerned here. Now, let me just say that this is a very old kind of, it's not a new, more holistic approach that's taken on nowadays, okay, concerning sustainable development, because nowadays it's still about, the focus is still about intergenerational justice, but it's not only about intergenerational justice. Nowadays, it's more about inclusive growth, inequality, therefore compatible clearly with environmental resources. Okay, but it's more holistic approach rather than only focused on the issue of intergenerational justice. Okay, so therefore clearly also the policies are very different. But for what we are interested in here, this is well, it's quite fine. Also, later on we'll discuss the issue of climate change. So we're going to see a very simple model of climate change and what are the policies therefore that that we need to be in place in order to mitigate the climate change problem, and clearly for this proposed this definition is quite acceptable. Okay, but just to let you know, that's not what's how sustainable development is viewed nowadays. Okay, okay, so here. This is concerning the sustainability criterion, concerning the economy's production possibility. What we are here concerned about, in particular, two issues. One is technical progress, and the other is population growth, okay, because they are going to impact on sustainability, as we are going to see, okay, in kind of opposite way. Okay, let me go straight to the results. And then I'm going to show you how this can be formalized and studied formally. Okay, so these are the results that are in the literature. Okay, then later on I'm going to calculate explicitly one and show you explicitly one of these models. Okay, so clearly the simplest one, which is this here. So assume that you have a Cobb-Douglas production function, Now, if output is produced in a fully competitive way, with constant returns to scale, and you have two inputs, the capital that is clearly reproducible because it's manufactured, and then you have the non-renewable resource R. So you have a production function like we have seen last week, okay, if you remember. This has, if you remember, this has an elasticity of substitution equal to 1. Then, in the absence of technical progress with constant population, it is feasible, one can show that it's feasible to have constant consumption across generations as long as alpha is greater than beta. Okay. I'm going to show you how this is feasible later on, okay? Even though I won't go into the specifics of alpha and beta, but I'm going to show you that that with constant elasticity of substitution, with elasticity of substitution equal to 1, you get sustainable development. Okay. Now, the more complicated model is clearly with the constant elasticity of substitution production function we have seen last week. Again, two inputs, R and K. And in this way, you get remember, this is something I've tediously, I would say, calculated last week, okay? So you get a constant elasticity of substitution of 1 over 1 plus theta, okay, if you remember. I've calculated this explicitly last week. And so changing the parameter theta, you have, you change the curvature of the isoquant. And in this way, you change the elasticity of substitution. And one can show is that, again, in the absence of, so without technical progress and without population growth, it is feasible to have a constant consumption across generations if this elasticity of substitution is greater or equal to 1. Okay, so if it's greater or equal to 1. So what's the meaning of this? Okay, remember, if sigma is greater than 1, this means, okay, if you remember the unfortunate and tedious calculus I've done last week, okay, then the input is non-essential. Okay, if sigma is larger than 1, then the input is not essential. Okay, and it's quite obvious because when is theta, when is sigma larger than 1? It is when theta is negative. If theta is negative, then you can see, I mean, it's quite obvious that here the inputs are non-essential. Okay, so you can just set R, for instance, equal to 0, and you can still produce a positive amount as long as capital is positive. Okay, so the input is not essential. In the case of sigma being equal to 1, then it's also something I've discussed last week. The constant elasticity of substitution production function collapses to the special case of Cobb-Douglas production function. Okay. This can be shown, remember, yes, but by looking at the elasticity of substitution. Okay. So the properties are identically the same. Okay. And therefore, we have seen that Cobb-Douglas means that you get substitutability. Okay. So therefore, here the result is the following. Okay, I'm going to repeat this later on, but the result is that as long as elasticity of substitution is sufficiently large, meaning greater or equal to 1, you get the sustainability. Okay, you get sustainability. Is it clear? It's quite intuitive also from the discussion we had last week. Okay. So it's quite intuitive. You need, if you remember, you need sufficient degree of substitutability in order to be able to substitute over time more and more of the non-renewable resource with the renewable one. Okay? And therefore, the elasticity of substitution, the elasticity must be sufficiently large. Okay? and here the key value is 1. Otherwise, what you need is a backstop technology. So what is a backstop technology? A backstop technology is a technology that you can use and in this way do completely without the non-renewable resource. Okay, so there is a technology that is available, and by switching to this technology, you can do completely without the non-renewable resource. Okay, so this is another way to say that the non-renewable resource is non-essential. Okay? Okay, so let me repeat this. So the backstop technology is a technology that is available. The only thing is that it's very costly. Okay? But it's there. And so what you can do is, if the non-renewable input becomes sufficiently costly, you can switch to from the current technology to this backstop technology, and in this way you can completely do without the non-renewable resource. And so the problem here becomes, if you want, from a theoretical point of view, defining what is the optimal switching point. Okay, so this is kind of, let me give you an intuition. Okay, it's like having an outside option. Okay, so we know we are in a bad shape because we are going down a very dangerous road. Okay, so a very slippery road. So we don't know, okay, we know we're on the wrong path, but we also know that there is an outside option. Okay, this outside option is this backstop technology, and what we can do is, therefore, we can define what is the optimal timing to switch from the current technology to this backstop technology. Clearly, this is not only interesting from a theoretical point of view, this might also be interesting from a practical point of view, because if such backstop technologies exist, from a policymaker's point of view, the issue is then, once we know that there exists this optimal switching time, how can we, if we are interested in doing so, how can we make this happen earlier rather than later? So what are the policies such that a switch from the use of non-renewable resources to this backstop technology occurs earlier? Again, why might this be interesting? Because if the usage of non-renewable resources is, so the use of the non-renewable resource can be polluting, can be polluting, and that is, can pollute the environment, can lead, for instance, to climate change. So in this way, so just by, for instance, think about fossil fuel that pollutes the environment. So in this way, if there exists this backstop technology, again, policymakers could try to hurry up, try to favor the switch from fossil fuel, use of fossil fuel, to other alternative energy sources, and which is a kind of a backstop technology. Okay, so that's why estimating this option value, estimating the optimal time of switching of firms, okay, is important for policymakers. That has been done in the literature. Okay, so those of you interested, there is a literature on backstop technologies, evaluating these options and estimating, therefore, what are the policies that lead to a faster switch from current technologies to polluting technologies to future, let's say, less polluting technologies. Okay, that's why this is in. Okay, so just as a final comment here, therefore sustainability is feasible But clearly this can come at a cost, in the sense that since switching is costly, switching from current technologies to this backstop technology is costly, what might happen is that it might not be possible to maintain the same level of consumption. Okay? Therefore, there's for sure a cost, and therefore you might also have that then the economy, I mean, on the new, once the economy is placed on the new path, the development is the same, so the growth rate is the same, but still you might have a lower GDP and therefore lower consumption, okay, because you switch. So this is also common consensus in the literature. Okay, since there is this cost of switching, you might end up having lower consumption even though the growth rate is the same. Is it clear? So you have just to draw you here a picture. Okay, so what might happen here is, so if this is the, for instance, time, this is log of consumption. Okay, so if this is my consumption path, okay, so meaning that you have exponential consumption, okay. Okay, log C, okay, sorry, ft. What here might happen is that, so this is therefore the growth rate. So the slope of the straight line is the growth rate of consumption. So if you decide to switch at time t star, okay, if this is optimal switching, what happens here is that you have a decline in consumption and the growth rate might be again the same, okay, because of innovation, okay, because once you switch technology, there is no more market share for old technologies, and therefore innovators will improve the new technology. Okay? That's why all R&D expenditures switch from old technologies to these new technologies, and that's why the growth rate intuitively, okay, there are models that show this. So intuitively, the growth rate will be the same, even though you see there's a cost in doing so, having lower consumption, okay? Having lower consumption here, and but then the growth rate is again the same. Is it clear? Everything clear? And then, as I said, okay, T star might depend on, I mean, usually depend on policies, okay? And therefore, the issue for policymakers is try to find optimal policies such that you can reduce the optimal switching. This is in particular important if you are concerned with problems like climate change, pollution, or so on. They would like to have earlier switching rather than later switching.
Do you have any example of flexible technology?
Yeah, there are many. I mean, you can think about all the energy sources that are based on fossil fuel and try to switch from fossil fuel to renewable energy sources. They're costly. They're very costly to redesign production. Costly to redesign production processes. Okay, if you have to do without fossil fuel. Okay, and yeah, then I'm not very into, I mean, they're also talking about other energy sources like yeah, the thing I'm most familiar with is solar energy, but then also you have hydrogen and other, but I'm not so familiar with that kind of technology. But if you're interested in some real world examples, okay, there are some papers that estimate, okay. Okay, so you have switching from, and they are mostly related with switching from fossil fuel based energy source on to renewable energy sources. Okay, and they do the calculus, try to estimate. So they build the model, then you simulate the model, and then you do some policy estimate, policy simulation. Okay. Yeah, then if you're interested in, okay, some of some of this, I discussed some of these issues more in the development economics course. Okay, there I discussed one of the model, and I discussed also some empirical results on it. Otherwise, just drop me an email and send you the papers. Okay, it's always working. Okay, if you're interested in reading it. Okay. So now let me see how. Let me just discuss some further issues, and then I conclude here, and I'm going to see some formal results on this. Okay, so here, therefore, I have not yet discussed the issue of technological progress. So how does technological progress affect sustainability, and how does population growth affect sustainability? And it's quite intuitive that technical progress increases the range of circumstances where you have sustainability. So having therefore strong technical progress increases the cases where a sustainable development is feasible. On the other side, it's quite intuitive, okay, because remember, what is technical progress? Technical progress enlarges your consumption, your production, and therefore consumption possibilities. Technical progress means that you can produce the same output with fewer inputs. Okay, and that's exactly what you would like to do, okay? Because remember, you have a non-renewable resource. We have a non-renewable resource, and therefore, in order to have, if it's essential, we need to have some of these resources also in the future, and that's why we have to do, over time, we have to do with a smaller amount of this resource. And technical progress is exactly what helps you in this sense, because technical progress tells you that you can produce the same amount with fewer inputs. And that's exactly what we like to have, okay, if you are dealing here with a non-renewable resource. That's why it's quite intuitive that technical progress is clearly here lending a hand in this sense. Population growth. Population goes in the opposite direction, because clearly, if there is population growth, then what you would like to have is constant per capita consumption, and therefore, the more individuals there are, the more output you have to produce, and the more output you have to produce, the more inputs are needed. Okay? And that's why you see this goes in the opposite direction. Okay? Since you need more output because of a growing population, you need more inputs, and this clearly goes in the opposite direction. Okay? And therefore, the stronger population growth, the more difficult it is to obtain sustainability. And therefore, in this case, what you need is sufficiently strong technical progress. Okay? Otherwise, it's not feasible. Okay? Because technical progress now has to offset the negative effect the population growth has on input requirements. Okay, is it clear? Final issue is what happens if sigma is lower than 1. Now, if sigma is lower than 1, then you can have sustainable development, but in this case, you need sufficiently strong technical progress. Okay, you need sufficiently strong technical progress. And again, this is quite intuitive, because remember, if sigma is lower than 1, means that the degree of substitutability is very low. And therefore, as the economy evolves, you can't really do, if you want to keep consumption constant, you can't really do with a lower amount of input. And that's why you need sufficiently strong technical progress, because sufficiently strong technical progress allows you to use a lower amount of inputs over time. Okay, that's why the lower degree of substitutability, the stronger the technical progress has to be. It's quite intuitive. And clearly, if you have in addition to this, if you have also population growth, then the pace of growth of technology has to be even larger. Okay, so this is the general result, and it opens up also another question we are going to see here. So what is there for the general conclusion? The general conclusion is that sustainability requires either a relatively high degree of substitutability between inputs and the non-renewable resource, or a sufficiently large technical progress, sufficiently large growth rate of productivity, or the presence of a permanent backstop technology. Okay, this is the general consensus of the literature here, if you look at different results. Now I'm going to, as I said, now in the following, I'm going to show you what are the conditions such that you have an optimal use of the non-renewable resource. Okay, so what are the requirements? Okay, if you want to solve in an optimal way the intertemporal and intertemporal trade-offs that you face. Okay, I'm going to show you this from a formal point of view, something that we have seen here just from an intuitive point of view. Okay, and then I'm going to show you an example of sustainability. I'm going to show you in the particular case of Cobb-Douglas production function. It's very simple to solve the model explicitly. I'm going to show you how to get the sustainability. But then I'll also answer another question, which is the question here, and it's a different issue. Okay, so given that sustainability is feasible, is sustainability also something that is desirable from a social point of view? Okay, because remember, sustainability is just a condition that consumption is non-declining over time, or output is non-declining over time, or capital is non-declining over time. Okay, this is sustainability. Okay, but the other issue is this also something that is socially desirable or not? Okay, that is to say, the conditions we are going to see now of social optimality, so solving up in an optimal way the intertemporal and intertemporal trade-offs, are these conditions compatible with sustainability? Okay, I would like these two to be clear. Okay, is it clear that there are two? Okay, I try to stress this because over the past years, okay, when I asked this in the exam, okay, sometimes I got really confusing answers. Okay, so there are two issues. Okay, so the efficient and optimal use of non-renewable resources, which deals with the problem of solving in an optimal way the intertemporal and intertemporal trade-offs. Okay, so loosely speaking, it's about intergenerational justice. Okay? But then having sustainability, which means that imposing a constant consumption or non-declining consumption path is an additional constraint. Okay? It's something that is on top of the problem of solving in an optimal way the intertemporal and intratemporal trade-off. Is it clear? And therefore, having this additional constraint, so this non-declining consumption, non-declining output, non-declining capital stock, or whatever you want to define sustainability. Therefore, this can be conflicting with the optimal and efficient, socially optimal use of non-renewable resource. Okay, and therefore we have to see what are the conditions such that the two do not conflict, such that the two are compatible. Is it clear? Okay, because now I'm going to show you some models, and therefore it's just being some math, and that's why something's not clear. Okay, now it's not going to be clear, I guess, from now onwards. Everything clear? Okay. So now let me tell you what I'm going to do here. Okay, so I'm going to, first of all, discuss going to present you the model we are going to see here, okay? Try to state the problem as clearly as possible and give you also some intuition wherever this is possible, okay? Then I'm going to solve the problem formally up to a certain point, because the only thing I'm interested here is in these trade-offs, okay, we face intertemporal trade-offs. And I'm going also to characterize some of the, I'm going to give you some results on the optimal consumption path. Okay, so we are going to see here the optimal resource extraction path in the presence of non-renewable resource and the optimal consumption path. Okay? And we are going to do this from a social planner's point of view, because this gives you results in terms of what should happen, okay, if resources are used in an optimal way from a social point of view. One can show that the decentralized solution is not that different, okay. I mean, the main results are very similar, because they're not too dissimilar. But clearly, a social planner is more important because it tells you what the first best is. Okay? And therefore, first of all, you should study the social planner, and then what a competitive or non-competitive economy does, because then you know what are the distortions introduced by a non-competitive versus also a competitive economy, for instance, if there are any. Okay, that's why the social planner is kind of. So what are we going to see here? What is the meaning of social planner? Social planner here means that we're going to have a social welfare function where utility of individual is discounted. Okay, so you have a utility flow of generations that is discounted, and what you therefore do is you calculate the present value of this utility flow over time. And you do this, you calculate the present value with using a social discount factor. And then given the social welfare function, what the social planner does is the social planner optimally chooses consumption path and resource extraction path. The constraints here, I mean, there are two constraints in particular. One is the resource constraint. I mean, this is what I've already now kind of discussed, okay, over the past lectures. So the resource constraint is that what is extracted today is no longer available tomorrow. This is going to be a dynamic constraint, clearly. Then you have also another dynamic constraint, and that is the constraint of capital accumulation. So what is consumed today is not going to building up capital, and therefore you have fewer consumption and production possibilities tomorrow. Okay, so what is consumed today, the more is consumed today, the less is saved and hence invested. And so therefore you have lower consumption possibilities tomorrow. Okay, these are the two constraints we have, and they are two dynamic constraints. Okay, rather than being static constraints, what you have here is dynamic constraints. Okay, therefore, since you have dynamic constraints, I'm going to solve the model using optimal control techniques. Now, so seeing your look, you have never seen this. You have. Yeah, you saw this in mathematics, okay? I hope so, at least. Okay, well, I give you a refresher. Here you have a, I'm going to refresh your memory, and then also later on I'm going to use the first order conditions, and then I'm also going to solve explicitly an example. Okay? And so you have also kind of an mathematical exercise. So what is now here the social planner's problem can be expressed in terms of an optimal control problem. Okay? This is the general setup, and then I'm going to give you the general result, and then I'm going to set up our problem, and I'm going to solve our problem. Okay, now. So this is therefore the optimal control problem, which is usually stated in the following way. You have an objective function, which is expressed as an integral of a flow of rewards. Okay, so meaning that what you gain. Okay, so flow of gains over time. The only thing that you have to do here is you have to take the present value. Okay, so f is my objective function, so the thing I would like to maximize, and since time stretches from 0 to infinity, and I'm remember integral is just like summing, but not in discrete time. It's summing in continuous time. Okay, so here having the integral means just that I'm summing. I'm summing here this f, the value of my f function in time, not in time 1, 2, 3, and so on and so forth, but in time t plus dt, t plus twice dt, and so on and so forth. Okay, where this dt goes to 0. Okay, that's summing. Okay, summing in continuous time. Since I'm summing a positive amount, I need this integral to converge. That's why I have to. Usually, what I do is I take the present value of it. That's why I have a discount factor here in front of it. E to the power of minus rho t is my discount factor. Okay. Now, here I have, so what I'm doing here, I'm maximizing this function f, choosing c, which is my control. Okay, c is my control variable. C is my control variable. And you have to choose, therefore, c in each time period. Okay, it's like, so think about, so you can think about it in terms of a discrete time problem that is transformed into a continuous time problem. Okay, therefore, here in discrete time, you would have time 1, 2, 3, 4, and so on and so forth. And therefore, in each time period, you would have to choose control at time 1, control at time 2, 3, 4, and so on and so forth. The only thing here is that you don't have time 1, 2, 3, 4, and so on and so forth. What you have is you have to control at time t, t plus dt, t plus twice dt, and so on and so forth. But from an intuitive point of view, it's the same. Okay, each time period, which is infinitesimally small, you have to choose my control. Okay, is it clear? Yes, later on it's going to be both extraction and consumption. Exactly. Yes, my C here is just the control, meaning that I'm going to control my problem. Okay, but then from an economic point of view, I'm going to have two controls. Okay, the how much of the resource I'm going to extract, and how much of my output I'm going to consume. Okay, because I have two intertemporal problems. Remember, from an economic point of view, I have two intertemporal problems. On the one side, the more I extract, the less is available tomorrow. Okay, and therefore I have to decide how much in each time period to extract. Knowing that the more I extract today, the less is available tomorrow. But then I also have to decide how much to consume today, knowing that the more I consume, the less will be saved and the less the lower is the amount of capital tomorrow.
Sorry, so we want to maximize that function where f, for example, for practical terms, everyday utility.
Exactly. If it's the social plan,
utility is subject to the actual state of the resource that we are consuming.
yes.
So
no, because it's why should the utility directly depend on the resource? Usually, utility depends just on consumption.
Okay, the first term of f is consumption.
Yeah. So you don't like this, okay? But just, let me. Okay, now let's continue. Okay, now just to give you.
is the extraction rate.
Yes, but I'm going to show you later on. I have two contours, not just one, because I have also consumption. Okay, because also this influence, as I try to explain. Okay, so the more I consume today, the less get invested, and the fewer are the production possibilities tomorrow. And I also remember there is a certain degree of substitutability between capital and the resource. Okay, and this also therefore affects how much I should consume today, knowing that I have to substitute capital with the resource. Okay, that's why the problem is a little bit more complicated than your. And I'm just going back to your problem. F could also be profits. Okay, the problem we are going to see is from a social point of view. That's why it's going to be consumer welfare. But you could also set up the problem in a decentralized way, where firms choose the optimal extraction path, okay, maximizing their profits. Okay, that's something we are not going to see, but if you want, I can give you the references. I studied in the literature. You get slightly different result, okay, but intuitively it's very similar. Okay, it's just the social welfare is the first best. Okay, clearly, and that's why all the deviations should be measured in terms of how far we're away from the social. And that's also important if you think about taxes. Okay, and if there are any things that have to be corrected, they have to be corrected knowing what the first best is. Okay, that's why the first best is that important. That's why we start with the social welfare problem, the social planners problem. Okay, we're going to see this. Okay, let me just give you a refresh here of the optimal control problem. So here, therefore, I choose my control in each time period, and knowing what? Knowing that, well, my f function could depend on c, okay, the control, but what it for sure could depend on is the state, okay, because my control affects the state, okay, and the state can affect my my objective function, okay, and therefore that's for this, and this usually is a dynamic constraint, okay. So therefore x is my state variable, and therefore what the actions I do, the action I take today affect my state, how the state changes, and therefore it affects my objective function. So this is the sense of this differential equation. Okay? Then let's go faster here, because then I can go to the economic example, which is clearly more interesting. But I need just here to be everybody on board, okay? Because then you're going to use my first order conditions. Then how to solve this dynamic optimization problem. Now, what you have to do is you have to build what is called a Hamiltonian function. Okay, this is the Hamiltonian function. It's very similar to what you're perhaps more familiar with, the Lagrangian function. Okay, indeed, one can show. I don't know. Have you seen the proof of optimal control first order conditions in mathematics, or you just saw the result? You forgot. No, sorry. You just saw the result. Okay, for those of you interested, you can show that you can get the first order conditions you saw in mathematics, or they are depicted here, starting from the static optimization problem. You can, therefore, there is the problem is very similar, okay, but you can write everything in terms of a static optimization problem, and in this way derive these first order conditions here. Okay, that's something I'm not going to do, but it's important in order to get some intuition of why we get certain results. Okay, Okay, so how to write, because also how we write the Hamiltonian is very similar to how we have written the Lagrangian. Okay, you see, the problem is very similar because you can switch from one to the other. Okay? So what is the Hamiltonian? The Hamiltonian is here, first of all, my objective function plus lambda, which is my dynamic multiplier, times the constraint. Okay, the constraint here, remember, was my g function. Okay, this is how you set up the Hamiltonian function. So therefore, here, lambda is my dynamic multiplier, or also what is called the co-state variable, because for each state variable you have a co-state variable. So if you have more than one constraint, more than one dynamic constraint, you will have more than one co-state variable, because each state variable has a co-state variable. Indeed, the problem we're going to see has two dynamic constraints, and therefore we'll have two co-state variables, okay? Two dynamic multipliers. Okay, and these dynamic multipliers, like the Lagrangian multipliers, have economic meaning. Okay, and they're going to be exactly the same as we have seen in the case of Lagrange. Okay, for those of you who have attended the lecture on a couple of weeks ago, I guess, where I solved the dynamic static optimization problem. We have seen, okay, the meaning of the static multiplier. Okay, here I'm not going to prove it because it's much more complicated. Okay, but given that the problems are very similar, it's quite intuitive. Okay, the economic meaning of the dynamic multiplier. Okay, so what are the first order conditions? So what I have to do in order to find the optimal conditions? Okay, here I have what are called static efficiency conditions and dynamic efficiency conditions. And why are they important? Because our static efficiency conditions means that we solve in an optimal way the static trade-off, the intertemporal trade-off. Dynamic efficiency conditions are about the intertemporal trade-off. Okay? That's why, since we have here, as I tried to explain now at some length, we have intertemporal trade-off. I need both static and dynamic efficiency conditions. Okay. Now, what is the static efficiency condition? The static efficiency condition is just maximizing my Hamiltonian function with respect to the contour. Okay. What is the dynamic efficiency condition? The dynamic efficiency condition is a little bit more complex. Okay, it gives you an implicit optimal path. Okay, for the dynamic multiplier. Okay. And the dynamic path is the following. So the dot, so the letters with the Greek letters with the dot, or letters with the dot, okay, means that they are time derivatives. Okay. So this is lambda dot equals rho lambda minus the derivative of h with respect to x. Okay. This is how you solve the intertemporal trade-off. And then, last but not least, you have also another condition that's just given by the law of motion of your state. You would also have some boundary conditions, okay? So that's something I'm not going to discuss here because I'm never going to solve explicitly for paths, okay? For paths. Just to say, okay, here you have to give you an intuition of why we are still missing something here. These are differential. So here we have two differential equations and one static condition. Okay, so as you know, the differential equations give you. What I'm looking here for is I'm looking for a time path for x. Oops, I'm looking for here a time path of the control and my x. Okay, this is what I'm looking for. Okay, for t, it goes from 0 to infinity. Okay, this is what I'm looking for. So I'm not looking for a scalar, but I'm looking for a function, okay, of time. And this can be obtained by solving these equations. And yeah, implicitly, clearly, I also get clearly a path for lambda, okay? Yeah, because I have three equations and therefore three unknowns. Okay, these are the three unknowns: c, x, and lambda. Okay, and you can imagine, since two are differential equations, I get many functions. Okay, because as you know, once I differentiate, I get the result up to a scalar. Okay, because if you take the time derivative for constant, it is zero. Okay, that's why you get the solution up to a scalar. That's why in order to fix exactly one path, you need what are called boundary conditions. Okay? So what happens at the end? Okay, usually these are called in mathematics transversality conditions. I don't know if you have heard about them. Okay, if you have not, okay, just forget about what I mentioned. Okay, because I'm not going to use transversality conditions here. But if you are, I mean, if you read growth theory, if you read papers, okay, many have these transversality conditions because remember, it's quite intuitive. You solve differential equations, and what you get is you get paths. The time derivative on the left and the right hand side of this equation. Okay, I can take time derivative. So on the left and the right, and the equation still clearly has to be true. Okay, because this is the constraint I'm facing. Okay, so this is the constraint I'm facing, and I can take the time derivative on the left and the right. So on the left, it's just s dot, okay, because s dot, remember, is just the time derivative. And on the right, you see the derivative of this, well, S0 is just a constant. The time derivative of a constant is 0, clearly. And the derivative of this integral is just RT with a minus clearly in front, because I have minus here. Now, what's the intuition of, those of you who know calculus, okay, yeah, for sure. They have for sure already made up their mind. Now, for those of you who are not that familiar with, okay, this result is quite intuitive. Okay, so how does the resource change at time t? Okay, because this is what this resource constraint here tells me. So how does the resource change at time t? Well, it depends on how much is at time t extracted of the resource. Okay, this is what this constraint here tells you. Okay, so the left-hand side tells you how much, by how much does it change? Well, it changes depending on how much you extract. I'm lucky also today. Okay, is it clear? So by how much does it change? It depends how much it gets extracted. Okay, the more you extract, the greater the change. Okay, everything clear? Now let me go also over the other constraint, and I will tell you what the problem is, and then let's take a break and solve the problem after the break. Okay. Now, what is the second constraint? So I don't have, so in this case, it's not just one dynamic constraint, but I have two dynamic constraints. So the first we have just seen is a resource constraint. What is consumed today, we see here, what is harvested today is not available tomorrow. This is what this equation tells us. Now, I have another constraint. And the second constraint, intuitively, as I said before, the more you consume, the less, the lower the saving, the lower the investment, the lower the amount of capital tomorrow, and the lower the amount of capital tomorrow, the lower output production possibilities tomorrow, and therefore consumption possibilities tomorrow. So how can we write this down formally? Okay, here we have a closed economy with no government expenditures. So closed economy with no government expenditures, we have the following accounting identity. So that is to say, output is either consumed or invested. Okay, this is an accounting identity. Okay, so this is true by definition, okay, how things are defined. Now, what is just capital change over time? Assume no depreciation. So assuming that there is no depreciation, capital changes just according to its investment. Okay, so how much I invest. Okay, yeah, I have no depreciation. Okay, this is an assumption. So capital never gets obsolete. Okay, or it maintains its value. Okay, this is clearly a simplifying assumption, but would not change and here the results in any important ways. Okay, so then from from this accounting identity, what I can calculate is, I can calculate what investment is. Investment is just output minus consumption. And remember, this is savings. I don't want to, yes, let me just write it here, save. Okay, this is savings. If you remember in from macroeconomics in closed economy, the capital accumulation equation. Okay, so this is how capital gets accumulated over time. Okay, those of you who have taken some growth models, growth theory, are very familiar with. Okay, and here you see the trade-off I mentioned before. So the more you consume, the less you save, the lower the investment, and therefore less of capital gets accumulated. And clearly, if lower amount of capital gets accumulated, you have fewer production, therefore consumption possibilities tomorrow. And this is another intertemporal trade-off we are going to solve in an optimal way. Okay? Is it clear? Okay, now let me just state the problem and explain it, and then we'll start. Okay, so therefore this is my social planner's problem. So the social planner has to solve in an optimal way this constraint maximization problem. So that is the present value of utility flows subject to two constraints, dynamic constraints. So one is the resource constraint that tells me how much of the resource is left, or put differently, the more I extract today, the less is available tomorrow. And my capital accumulation constraint that tells me the more I consume today, the less gets saved, invested, and therefore fewer capital is built up over time, which leads to lower consumption and production possibilities tomorrow. Therefore, what the social planner here has to do is, the social planner has to choose two contours. Okay, so one is the consumption at each point in time, the resource extraction rate at each point in time. So these are my two contours. Okay, two contours. The social planner has to optimally choose how much to consume in each point in time, knowing that the more is consumed, the less is saved, the less is invested, and therefore lower amount of capital is built up, and therefore fewer consumption production possibilities. The optimal extraction rate, the more I extract the resource, the less is available tomorrow. And since the resource enters the production function, the fewer of the if a lower amount of the resource is available tomorrow, lower amount can be used tomorrow, and therefore lower my production and consumption possibilities tomorrow. Okay, these are the other trade-off. And therefore, I have two contours and two state variables. State variables are S and K. Okay. S is the state of the non-renewable resource, and K is the state of my capital. Here you see, going back to your question, a previous question, I don't have R that enters my objective function. Okay, I don't have R that enters my objective function because I'm maximizing utility. But if instead I were to maximizing profits, I would have profits that depend on production and R, okay, and not consumption. Okay, so it depends really on what you maximize. Okay, so here you are we are dealing with a social planner, and therefore the objective function depends on C. But C clearly depends on both R. Depends on R and C. Okay? C also depends on R. That's what I would like to here to stress. Okay, because what just one final comment here. You see, this is my social planner's problem, where I try to find the optimal, so let me stress this, the optimal, socially efficient, okay, socially optimal, efficient extraction path and consumption path. Here you see, I don't have any constraint on consumption. Okay, I could also have here, as an optimal result, a declining consumption path. Okay, you see, I don't have any constraint on how consumption behaves over time. As a result, as I'm going to show you after the break, I could have also declining consumption path. Okay, which clearly is not compatible with the definition of sustainable development. Okay, because sustainable development requires non-declining consumption path. Okay, that is just to stress here the fact that defining what is socially optimal and efficient is not necessarily the same as what is sustainable. Is it clear? There are two different issues. That's why later on I'll talk about conditions such that the two are compatible. Okay? That is, sustainable development is also something that's desirable and it's socially efficient, socially optimal. Okay, is it clear? There are two different issues. Okay, there are no questions. For the moment being, I would like to stop here, and then after the break, I'm going to solve the model and give you the formal solution and also the intuitive solution. Okay, so what's the meaning of the first order conditions? Okay, from an economic point of view. So what are we doing? And implications. Okay, so have a nice lunch and talk to you in about half an hour if you want. Okay. All right, thanks. Okay, so let's start. Okay, here what I'm going to do now is solve formally this problem and discuss first order conditions from an economic point of view. Just the last comment, perhaps. Growth theory is based on this model without this equation. Okay, so maximizing the present value of utility flows subject to the capital accumulation constraint. This is the basic economic growth model. Okay, so that kicked off neoclassical growth theory and more modern endogenous growth. So therefore, what we are doing here is we are dealing with an economic growth on renewable resource. It's a little bit more complicated than the classical economic one. Okay, let's so okay. Before what we have to build a function, which is in this case my utility, because I'm maximizing here utility, and then I have constraints, the dynamic constraints. I have two dynamic constraints. So one is the resource constraint, and the other is the capital accumulation constraint. Okay, so and each of these constraints have a co-state variable. So P is the co-state variable of my resource S. So P is the co-state of S, and omega is the co-state of state K. Okay, remember I have two states, and therefore I need two co-state variables. And therefore I have to multiply the right-hand side of the dynamic constraints by these dynamic multipliers, P and omega. Now, what's the economic intuition for these co-state variables? It's similar to what I've said before the break. Okay, remember in the Lagrangian setup, if you remember what we have seen there, maximization of utility subject to the budget constraint. Okay, what we have seen there was that the Lagrangian multiplier was the shadow value of in the classical utility maximization problem, where you maximize utility subject to the budget constraint. What is lambda? Lambda is the shadow price of income. Okay, that's something I've shown you this formally. Okay, shadow price of income. Here, in a similar way, one can show that these co-state variables are shadow prices, and they are shadow prices of the stock variable. Okay, so therefore here you have two co-state variables. So you have P, which is the co-state variable of S, and therefore P is the price, the shadow price Of what you're maximizing. So if here you're maximizing utility, shadow prices are in utility values. If here you're maximizing profits, which are monetary values, then these are monetary shadow prices. Is it clear? So therefore, the unit of account of your shadow prices depends strictly on the object you're maximizing.
Mm-hmm.